Start.
Hello everyone. I'm Yukon Lee and I'm with Hilbert, yeah, and Rohit to introduce our design for Lab 9. It's a is a mini processor for the combining our FIFO and CPU GPU together, and I'm introducing the top module. And as you can see in the screen, the top module is first we have an instance of CPU and GPU that we combine the CPU and GPU together and let the CPU to control GPU. And there's some handshakes between the our top CPU module and the FIFO module, like the FIFO interface, so that the FIFO will tell the start offset in the memory and then end offset of memory, and it will send a data ready inside the CPU when it fetch a packet, and the CPU would send a data down signals to FIFO when it execute all of this. So this is our CPU GPU top, and this is our sorry, this is our FIFO. Yeah, so this is the FIFO. The FIFO connected to some hardwares in the FPGA to fetch a packet, and this FIFO instance is right in here. As we already described it in the lab 8, so I'm not going into it. And yeah, so it will communicate with the FIFO to get these signals here, and it will write the memory into words, and when it gets the signal down, when the CPU told that it execute a packet, it will start it to write the signals out, and the memories will send data into the FIFO, and the FIFO will send the package out. So this is our top modules that we combine this system together with some software interface with the general registers. And Rohit, no, and Hilbert will introduce about the CPU things. Rohit will introduce about CPU things, and okay.
Hi everyone, I'm Rohit. So now I'll introduce about CPU and GPU, how they are connected, and the handshaking between CPU and GPU. And we have also made enhancements to CPU so that it can receive control signals and it can receive control and it can receive information from FIFO, and it can control the GPU. So I'll share my screen now. Uh, Show more about. Yeah, as you can see, so this is our top level design of CPU and GPU. And on the left, you can see uh, we have a CPU. On the right we have GPU. So there is a parameter bus that goes from CPU to GPU, so which can be used to load the parameter registers of the GPU. So through this we can control like which kernel should be executed and all. And there is also a GPU run and GPU done signals from CPU and GPU. So this way we can control the GPU execution. Uh, and we only and both CPU and GPU share only one port of the D memory. So that is we are using a mux to share that single port between CPU and GPU. And as you can see here, we are using port B for to interface with CPU and GPU. And whenever the GPU run signal goes high, the CPU will be stalled, and the GPU will be executing. And in this duration, GPU will have access to the D memory. And once GPU completes the execution, so GPU will CPU will take over the control of the uh, ports of the data memory. Yeah. And I'll take you through the added instructions. Like we added extra instructions to support all these features. So first one is like loading to know the data offset where the packet is in the data memory. So before you, we have a common block memory that's for FIFO, GPU, and CPU. So GPU and CPU use it as a data memory, and to to know where the payload is, we have added a new instruction RDF. So what this does is it reads that uh, data from the FIFO start offset and FIFO end offset ports. So these are directly connected to the FIFO interface. So so the data present on these ports will be loaded into any of the registers that we want. And the next instruction is FIFO wait. So so this uh, so uh, so this instruction is used to halt the CPU. So when this instruction is executed, so CPU will stall and it will wait for the FIFO data ready to go high. So once the FIFO data ready goes high, so CPU will uh, resume the execution. And the last instruction that we added is FIFO done. So when we when we modify the packet and when we are done with all the operations, so we will execute this instruction FIFO done. So this will send a pulse on the FIFO data done. So the pulse will be high for one cycle. So this will be used by the FIFO interface. And once the FIFO data done is high, so the packet will be delivered to the output. Now, Hobo will tell, like, give you the demo of the hardware implementation. How we have will give you the implementation and the hardware demo.
Thank you, Rohit, and thank you, Yukun. I'm going to take you through how do we implement our test bench and also how can we implement this whole system on an FPGA. So first, let me share my screen, sorry. Okay, and this is our test bench. And as you can see, we are implementing the package. When we receive the package, we have the data in our data D memory. But this time we are not using just one single core, not only the CPU, GPU, but also the CPU, GPU, 503 of them. And we are trying to say, okay, so we are having this data and we use CPU to use GPU as a subscript, and we asked it, as Rohit say, we use the signal to drive the GPU to operate the system. And when the GPU done with data processing, it will send back a acknowledge signal, and we will check the DRAM at that time and to say if the data already been processed and if it's correct or not. And so let me run the test bench first, and let me do it. As we can see, the first here is we implement the data memory, and now we use CPU to drive the DPU, and we see we stop at here because the data are being processed by the GPU, and now we run again. So at this time, the CPU received the die signal, and we can check if the DMAM is already written, overwritten or not. So we need to copy these log files into we need to check this log file, but it's have so many warnings the same because we give the data memory the same clock. It doesn't matter. And let me use our script to do that. And I just copy the scripts into this original file and use the same Python script to process it. Let me do it again. Okay, this one. And as we can see, is the first test the file because the same like we have some difficulty processing the 0 times 0 using the IP core, but we actually don't use positive 0 to represent in the BF16 format, so it's okay. So we ignore this one. After this one, all the other data are correct. As you can see, this passed and this passed and also this passed. And for the test 4, 5, 6, we are testing if the untouched place in the DRAM being modified or not, because we can use this one to show that we can very correctly receive the acknowledge from the GPUs so that our system are doing really the handshake operations. So that is for our test bench simulation. And let me show the hardware implementation. Okay, so we use the Fedora system again to generate the bit file and pass the route, pass, and the timing, and we get the bit file. And let me download the bit file again. And let me download one of them. Okay, now the system being already downloaded. Okay, and we are using our script to do the initiate instruction memory routing for the CPU and GPU about our kernels and the CPU's instructions. And okay, as you can see, the CPU's, I'll just say GPU's instruction memory has been written, and also the CPU's. And we are going to use the script to check if the places we used in the simulation is the same as we do in the hardware. And let me check. Like we do the 20 as address for our output, and okay. Oh, this is wrong because we didn't run our system yet. So let me run the system first. Okay, now we reset the PC and we do the run and we stop it. And let me see. We check the result place. Also, as you can see, the data has been changed and is 4080, 4000, 4080, and 4120 at 20. So it should be the same as the 21, 22, and the 23 should all be 0. Yeah, that's correct. And let me check with this number with our test bench. So inside the test bench, we can see inside the test bench, we expect the 4120, 4248, and 4254. So it's the same. So which means the hardware implementation success. And that's all for our lab9 demo. And thank you for watching. And all the documents and the codes, also the test bench has been uploaded to the GitHub. And thank you for watching.